Hi, today I'm going to go over approximate integration. We're going to go over Riemann Sums, left endpoint approximation, right endpoint approximation, midpoint, Trapezoid Rule. And we're going to talk about the error bounds and Simpson's rule. And I do have 5 examples, as you could see. Let's get started. Approximate integration. Sometimes it's difficult or even impossible to find an antiderivative. If you notice that there is more rules or formulas for integration than derivatives or differentiation. We know that the definite integral is defined as a limit of Riemann sum. So any Riemann sum could be used as an approximation. But of course, if you apply the limit, it's going to be the exact, and that's how we got the integration. If we divide the interval from a to b into n subintervals of equal length, that's called delta x equals b minus a over n, then the Riemann sum will be approximation to the exact definite integral from a to b. Now, we usually take x sub I star as left point, midpoint, right, and so on. But when you apply the limit, it's not going to make any difference. For the left endpoint, as you can see right here, and we're looking at the left endpoint, starting from I equals 1 to I equals n. This is the interval a to b. A will be x sub 0 and b will be x sub n. Just by applying I equals 1, that's going to be 1 minus 1, which is x sub 0. So being in the first interval, considering x sub 0, that means you're looking at your left. Let's look at the last interval or subinterval. For the last one, we're going to use n. So if you plug in n for I, that will be n minus 1. So you're still considering your left point, which is right here on the left. That's the left end point approximation. For the left, again, with a graph, considering, let's say, the third subinterval, as we could see right here, we have 4 intervals going from x sub 0 to x sub 1, then from x1 to 2, all the way to 4. If you count them, that's 4 subintervals. Looking at the third, to find the area for that column or stripe, we have to have the base times the height. But the height comes from f of x sub 3 minus 1, which is f of x2. So you're looking at your left, you reach up to the graph, and you build the height. That's how we apply it. In case if you look for the right Riemann sum, still we're looking at the third subinterval. The width or the base is x3 minus x2, which is equal in amount for all of them, times f of x3. f of x3 is my right point, and that's how I reach up to the graph and build my stripe. For the midpoints, we just take the average of the points right here, and that's going to be in the middle, and that will be, as you could see, it's all f of x1 bar, f of x2 bar, f of xn bar. So we're looking at the points in the middle, or what's called average. That's the concept of the average. By the way, if you notice right here, we're gaining and losing points or area. Take a look at this right here. For the midpoint, we are gaining this portion, but we're losing this portion. And here on the last one, we are losing this, as you could see, but we're gaining this. So the midpoint is a good approximation. Where if you go back, you could see that we're losing that much for the right endpoint. And we're losing right here these ones, and we're gaining this much. Here, we're gaining this, we're losing this, and so on. So they are usually an approximation. But of course, some of them are more accurate or having less error compared to the actual answer. Here's example number 1. Use rectangles to estimate the area under the parabola y equals x to the second. We know what x to the second looks like. From 0 to 1. So if we are focused only from 0 to 1, we're looking at a graph like this. And the curve, as you can see, it curves up to go up to 1, 1. Now, if the exact area is called S, we know that it's contained within a square with a side length of 1, but we certainly can do away much better than just saying less than 1. Why? What do they mean? This is a square of 1 by 1. So the area of S should be less than 1. Something to keep in mind. So for the graph that is going from 0 to 1, that's my A, and that's my B. B is 1. To find delta x, you could go b minus a over n, which is 1 minus 0 over 4, and that's 1/4. So that's my start point. 1/4, add 1/4, add another 1/4, 2/4, 3/4, 4/4. I know 2/4 simplifies to 1/2, and 4/4 simplifies to 1. Looking at the third stripe right here, taking it to the side, delta x is 1/4, and the height will be to my right. As you can see, this is my right, and that's 3/4 to the second. Why? Because I'm building it from 3/4, plugging it in the function, and that is 3/4 to the second, and it's down right here for the convenience. Same thing applies to the other ones. For the fourth one, we're gonna plug in 1 to the second, and that's the height of the stripe. Counting them, we have the following: 15/32, which is 0.46875, and definitely it's less than 1, as we agreed on earlier. This time we're doing as left Riemann sum. Being in the third stripe, we have 1/4, which we agreed on as delta x, and now we are considering 1/2 to the second, not 3/4 like earlier. Earlier we took 3/4 because it's my right. Now we're taking 1/2. Notice on the last one, number 4, we are dealing with what? My left point, which is 3/4. And of course that's a way less than what we saw earlier. Why? Because we're losing this and this and this and even this. Okay? Now what we notice from here is the right Riemann sum is an overestimate and gave me this much. The left Riemann sum is an underestimate because we're losing, and we got this much. Our area should be in between, and that's what we have. So the actual area should be an amount less than 0.46 and greater than 0.21875. To be more accurate and have less error, we could divide the whole thing into 8 stripes instead of 4. As you could see, the first point that we're going to stop at is 1/8. So that's going to be 2 8s, 3 8s, 4 8s, 5 8s, 6 8s, 7 8s, 8 8s, which is 1. Doing the math, we could see that we're gaining here small portions and we're losing here small portions, so we should be more accurate. Now, it's kind of hard to graph it with more than 8 stripes. Imagine 1,000 stripes. So if we go from 10 to 20 to 30 to 50 to 100, then 1,000, notice what we have here. So we are close now to 0.33 to something, or 0.338 between them, where earlier it was a way off. And a good estimate for if you have the left and right would be taking the average of both. That would be a good estimate. The average of the right for 1,000 stripes would be 0.3333, as you could see, and at the end 5. That's closer. So to improve our results, we should maybe consider larger number, but that's not practical to do it as n equals 1,000 or 2,000, so on. Why? We're going to have some notes in just like a minute or two. Trapezoid rule uses the trapezoid concept. The formula is 1/2 times base 1 plus base 2, all multiplied by the height. And any trapezoid will have like 2 bases, as you could see. Base 1, base 2. And let's put this back. That's base 2. Base 1, base 2, and some height. It could be graphed sometimes this way. And that's actually what we have in our case. That's the height. Now, for a trapezoidal rule of 1 over x, a function of 1 over x, we have few things to consider. Delta x is going to show up. That's my delta x. Let me show you what's delta x. Delta x is going to be the green spots down below. Those are delta x. That's my delta x. Why we divide by 2? It comes from the formula itself. And notice inside we have 1, 1, 1 as coefficients, but everything inside has 2 in it. Why? Because of the following. I'll show you that in just a minute. Here we go. If you take the first stripes to the left side, as you can see, I'm numbering them 1 and 2 right here. That's this one and this one. And let's say you put them on the side. Notice that this green, or highlighted in green, is also here. It's a line that is shared by 2 stripes. Okay. Here's another view. So if you take the first one to the left, that's this one, and you take the second one to the left, notice that base 2 here is also base 2 here. It's kind of hard for the second one to call it base 3 and base 4 because the bases here are identical. That's the same. So the stripes are sharing the mid bases or the mid heights. Those are shared. That's why we see 2 here and we see 2 in our formula. That's where the 2 coming from. Now, example number 2 says use trapezoid rule and the midpoint rule with n equals 5 to approximate the integral. The integral of 1 over x dx from 1 to 2. Well, 1 over x is a function that we know how it looks like. It's called the reciprocal function. But we are just focused on 1 and 2 as our interval. So here's the graph focusing on the first quadrant only. So we're going to approximate this area of the function 1 over x from 1 to 2 using both methods, the Trapezoid Rule and the Midpoint Rule. We're going to partition 1 to 2, the entire interval, into 5 subintervals. So delta x will be b minus a over n. In this case, it's 2 minus 1 over 5, because b is 2 and a is 1. That simplifies to 1 over 5. Differently, I could write as 2 over 10, decimal point, 0.2. So this would be 1.2, because we're adding 0.2 to 1. This would be 1.4, and so on. We have n equals 5, a equals 1, and b equals 2. And we have delta x 0.2. Notice that we have f of 1. That's the first point ever, which is f of x sub 0. And it's down below right here. And then we have the twice mentioned. For the third interval right here, or third stripe, we have 2 times, everything is 2 inside, times f of 1.4. And this is 1.2, 1.2, 1.4, we're adding 0.4, and 1.6, 1.8, and then 2. So that's 1.4. Doing the math, I just want to save you some time from writing all these numbers. I have it displayed as you could see. And f of 1 will be 1 over 1. F of 1.2 is 1 over 1.2. F of 1.4 will be 1 over, and the 2 shows up from the formula, and so on. Moving on. For part B, we're doing the midpoints. Well, if I have 1 and 1.2 and 1.4, 1.6, 1.8, and 2, the midpoints are in blue down below. As you could see, that's the midpoint. Between 1 and 1.2 would be 1.1. Between 1.2 and 1.4, it will be 1.3, and so on. We know that delta x is 1 over 5, or 0.2, and f of 1.1 will be 1 over 1.1, f of 1.3, 1 over 1.3, and so on and so on. The last one here is 1.9. F of 1.9 will be 1 over 1.9. Notice for the midpoint, we're not dealing with 2's inside. It's just like 1. Those are just 1's. And the answer is 0.691908 as an approximate. Now, it turns out that there's some kind of error because we are overestimating or underestimating in both cases, the Trapezoid Rule and the Midpoint Rule. Now, if you notice down below, I am rewriting the formula by adding let's use different color. I'm adding this to both sides, so I could have the integration, the exact amount by itself. Same thing right here. I'm adding the midpoint approximation with n subintervals to both sides to have the integration by itself. Now, looking at these formulas, this right here and this right here, we could read this and relate to it. Take a look. The error in using an approximation is defined to be the amount, that's called error, that needs to be added to the approximation to make it exact. Now, the Trapezoid Rule is an approximation. It could be underestimate, it could be overestimate, depending on the curve, if it's concave up or concave down. Same thing for the midpoints. But the error could be positive or could be negative, because sometimes we are overestimating and sometimes we are underestimating. By finding that error, we could say, okay, let's go back and add it to our approximation to get the exact. Same thing right here. So by finding the error, add it to the approximation, you get the exact. So now we're talking about what type of error, how much is the error, and how accurate could we get to by partitioning the subinterval into n subintervals. I'll show you some examples in the coming slides. So it turns out if you go for n equals 5, 10, and 20, we have the left Riemann sum, the right, the trapezoid, the midpoints. Not only that, we have the errors in each one of them. The error in left, error in right, error in using trapezoid rule, and error for the midpoint rule for n equals 5, 10, and 20. 5, 10, and 20. There's a lot to say about these numbers, so I'm breaking it down to different slides to go over it. Let's take a look. Number 1, as a comment. We can make several observations from these tables. Number 1, in all the methods we get more accurate approximation when we increase the number of n. So going from n equals 5 to 10 to 20, we could see that we get closer answers compared to the previous ones. Not only that, but the concept here, and look at the errors. The errors are amount of error. They get smaller and smaller. If you compare the first line to the second line to the third line, look at this right here. It's very small. 0.0000, that's 4 zeros, 78. Over, and that's, or actually under, to be added, and that's a negative number with 3 zeros. Okay? But there's a problem by doing 20 for n, or 10, or 50, or 100. The problem comes from the following. So we have, it shows right here that a very large values of n results in so many arithmetic operations. Those calculations are not that easy, that we must be aware of accumulated round of error. So it's not fully practical, but we know that increasing n will give us better results. Number 2, and the coming observations are more important, I would say. Number 2 says the errors in the left and right endpoints, and you could tell that I'm circling them down below to show you. Left and right, so I want you to focus right here, are opposite in sign. The ones are negatives and ones are positives. And they appear to decrease by a factor of about 2. So when you go from 5 to 10 to 20, double the value of n, look at the numbers right here. It looks like from here I could see that 24 is becoming 12. Just like an idea to show you that, yes, we are getting down, the amount decreases by a factor of 2. Half of it, in other words. Okay? Number 3. Number 3, I'm looking at the trapezoidal and the midpoint errors are much more accurate than the endpoints, the left and right. See the errors right here are way smaller compared to these errors. So if you have the choice to be more accurate, you take the left and right midpoints, left and right approximation, or the trapezoidal and the midpoint. Of course, the trapezoidal are closer. You saw that from the graph. It's almost like going aligned with the graph. And the midpoint, of course. Number 4. In the trapezoidal and the midpoint rules, they're opposite signs. As you can see, we have opposite signs. Positives right here, negatives right here, and appear to decrease by a factor of about 4 when we doubled the value of n. Going from 5 to 10 to 20, it looks like the numbers right here. If you look at 12, it became 3. It's about, not exact, divided by 4. Number 5. The size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. Going directly on the same line, this is 12 and 24. That's about half. So it looks like the midpoint approximation gives us less errors, about half the errors that we get from the trapezoidal rule. 6, as you can see right here, is about 3. It's kind of hard to read the whole thing. We're just focused on some numbers like 6 and 3. If you notice, I'm underlining them. Now, following is the errors estimates for the trapezoidal and the midpoint rule. This is the trapezoidal, AT, and this is the midpoint, EM. E for errors and M for midpoint. We could tell that we're using the second derivative. If the second derivative absolute value is less than or equal to some number k, k shows up on the formula here and also here. And we're going from a to b, so inside we have b minus a to the power 3, b minus a to the power 3, but down below we have n to the second. One major difference is the 12 right here and the 24 right here. So it's kind of not too hard to memorize the AT and EM. They're pretty much the same, except the 12 and the 24. Let's apply the error estimate to the trapezoidal rule. Approximation in our previous example number 2. For part A, I'm doing part A as you can see now, which is the trapezoidal rule. F of x equals 1 over x. F prime, to do it, I'm going to rewrite this as x to the power negative 1 and use the power rule. F prime will be negative x to the power negative 2. And f double prime will be positive 2, because negative 2 is going to go up front. It's going to change everything to positive. 2x to the power negative 3, which could be rewritten as 2 over x to the power 3. Now notice that 1 or x is going between 1 and 2, which means we could say that 1 over x is less than 1. This implies that 1 over x to the third is less than 1, of course, even faster. Going back to our formula, we're trying to get this part right here. This part right here. The k part. To find the k part, I am going to go with the following. F double prime, absolute value, equals 2 over x to the power 3 absolute value, which is less than or equal to 2 over 1. And that's what I have, 1 over x to the third less than 1. I used it. And that's 2. So we can take now k equals 2. This is our k equals 2 from right here. For the formula on the right side, we could move on and use the following. For k, I'm going to write 2. For b, since we're going from 1 to 2, b is 2, a is 1, and n is 5 as mentioned earlier, which is right here. Let me show you. This is b, or n equals 5. Simplifying, we get the following. We get 2 minus 1 to the power 3 over 12 times 5 to the second, and that will give me 2 times 1 to the third, which is just 2, and down below 25 times 12, that's 300. Simplify that, that's 1 over 150, approximate to 0.006667. This is the error estimate using the Trapezoid Rule for the integral from 1 to 2 of 1 over x dx with n equals 5. Now we're going to go to part B. Actually, let's see if we're going to do part B. No, I skipped that because it's pretty much the same thing, except what's the main difference? The main difference, if you remember, I talked about it earlier, it's the following. It's instead of 12, you're going to deal with 24. That's pretty much it. So right here, instead of plugging 12, you're going to plug in 24. So for part B, it's going to be a waste of time to write everything here. It's identical steps, except you change this to adjusted with 24. That's it. Moving on. This is more interesting. Example number 3. It says, how large should we take n to guarantee that the trapezoidal and the midpoint rule approximations for the integral from 1 to 2 of 1 over x dx are accurate within 0.0001. To do this problem, we're still using the same formulas, but this time we're looking for n. How large should we take n? That's the question. So when it says within 0.0001, accuracy to within 0.001, as you can see, I added at the bottom side, means that the size of the error should be less than 0.0001. Here we go. To find n, that's n is missing, such that the error of the trapezoidal rule, we're focused on the trapezoidal rule just now for this slide, is accurate within 0.0001. The formula is rewritten to save some time from recording, as you could see, and now we are into the calculations. So we have k times b minus a to the power 3 over 12n to the second, and that is 2. We're still on the same function and the integral from 1 to 2. So k was determined to be 2, and we have 2 minus 1, and that's a 1 to the third over 12. We are writing n to the second, not 5 to the second. So the left hand side is 2 over 12 n to the second, and the right hand side, we want it to be point less than, that's within 0.0001. So we're solving for n. To solve for n, we could do a shortcut. Our focus is right here. We will switch this and this. We could do that, or you could cross multiply and leave n to the second alone. By doing that, we get the following. we get n to the second. I'm doing 2 steps in one. It's going to be on the right side with the greater sign to it if you read it from the right side, but I'm switching it over greater than 2 over 12 multiplied by 0.0001, and we're solving for n. This right here becomes n to the second greater than divide by 2 between 2 and 12 becomes 1 over 6. 6 multiplied by 0.0001, we have 0.0006. Taking the square root of both sides, I have n should be greater than 1 over the square root of 0.0006, which is approximate to 40.8. To finish the problem, we could say that therefore n equals 41 will ensure the desired accuracy. We can't take 40.8, of course. We need greater than 40.8, and 41 will do. Of course, if you think about it, like take n equals 1,000, 2,000, 1 million, for sure, but we want to see which n will put you in the borderline of 0.0001 accuracy. So 41 will do. Anything higher than 41, of course, will do that too. But the 41 is the start. Now, the second part is EM. We have the same concept. So we have the following on the right side. 2 for k. We have 2 minus 1 to the third, which is not going to make a difference because it's going to end up 1. This time we're using 24 instead of 12. And we are not using n equals 5. We're looking for n. To simplify this, we have 2 times 1 to the third, and we have 24 n to the second, and we need the accuracy to be within 0.0001. Switching n to the second and leaving it on one side by itself, doing 2 steps in one, I have n to the second greater than 2 times 1 to the third, which is just 2, over 24 multiplied by 0.0001. Let's go to the right side and finish it. So we have n to the second is greater than 1 over 12 if you divide by 2, 0.0001, multiplying 12 times 0.001 and taking the square root, I have n greater than 1 over the square root of 0.0012, and that is approximate to 29. So therefore n equals 29 will ensure the desired accuracy. As you could see, the calculations are about the same, except instead of 12, 24. That's the reason why I skipped the one from the last example. Moving on. Simpson's rule. What's Simpson's rule? Simpson's rule uses parabolas, as you could see. Another rule for approximation or approximate integrals results from using parabolas instead of straight lines. The one thing that you need to keep in mind, which is highlighted in yellow, is we assume that n is an even number. only even numbers. Simpson's rule as approximation to the integral, as you can see right here, we are dealing with delta x over 3, that's something to keep in mind, over 3, and inside, notice the numbers or the coefficients. I have 1, 1 at the front and at the end for f of x sub 0 and f of x sub n, and inside it goes 4 to 4 all the way and keeps repeating till the end, 4 to 4. So it starts with 4 and ends up with 4, eliminating the first term and the last term. 4 ends and starts with 4 and alternates between 4 and 2. Something to keep in mind. Use Simpson's rule with n equals 10 to approximate the integral from 1 to 2 of 1 over x dx. Keep in mind that we are dealing with 3 here, delta x over 3, and we are dealing with n equals a number that is even. To get you started, I wrote enough notes to save you some time from the video recording. F of x equals 1 over x, n equals 10, delta x equals b minus a over n. So we are looking at b minus a, and we're dealing with the same function earlier, 1 and 2, from 1 to 2. So that's going to be 2 minus 1 over n, n is 10. And if you simplify that, that's 1 over 10, which is 0.1. The integral from 1 to 2, 1 over x delta x will be approximated to Simpson's rule with n equals 10. The formula is written in the box on top. On the right side, we just have to fill it in. Let's use different color to show you the numbers where they come from. So we have delta x over 3. So this right here will be 0.1. And inside, we have 1 times f of x sub 0. And the numbers will go like this. We are going from 1 to 2. And we are dividing this into 10 subintervals. So we have 1.1, 1.2, all the way to 1.9, then 2. So the first one will be plugging in 1. Let's take it back. It came up to be the eraser. That's going to be f of 1. This will be 1, f of 1.1, f of 1.2. Notice the 4 to 4 inside. F of 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and f of 2. Now, f of x is 1 over x. So all what we need to do is write the 1, 4, 2, I keep them in red, the coefficients. So we have f of 1, which is 1 over 1, f of 1.1, which is 1 over 1.1, f of 1.2 will be 1 over 1.2, and we'll just move on. Takes a lot of calculations, but that's how we start. 1.5, 1.6, 1.7, 1.8, 1.9, and f of 2 is 1 over 2. Using a calculator to approximate this, I have it on the side, which is 0.693150. And that should do it. To get 10 subintervals, n equals 10, just make sure that inside you count 11 terms, because you're considering 1 and 2. That will make it 11 terms inside. Something to keep in mind. We're almost done. Notice that in example number 4, Simpson's rule gives a much better approximation. S sub 10, Simpson's, sub 10, gave us 0.693150 in the previous slide. That's right here at the bottom. But we could integrate 1 over x from 1 to 2. Why? Because that's like du over u formula, which gives you ln. Plug in 1 and 2. Ln 2 is approximation to 0.693147, I believe. 7 or 3? 7. And ln 1 is 0. You could see from the graph that the graph goes through 1, 0, the x-intercept. So the actual is ln 2, which is right here. This is the actual, and this is the estimate using Simpson's rule with n equals 10. They're too close, as you could see. However, the Trapezoid Rule gave us this number, but you could tell that Simpson's rule is more accurate. The fourth digit is 1, just like the actual one, not 7, as you could see right here. Or even the midpoint. The midpoint gave me 0.69, then after that it doesn't match. It's not 3, it's 2. It turns out that there is a relation. The formula is down below. It's some kind of average between the Trapezoid Rule, the Midpoint Rule, and the Simpson's Rule. The error bound for Simpson's Rule is written down below, but notice I have the highlights for you to save some time. It shows the following. One thing is mentioned on top. By the way, the second table shows how the error ES is in Simpson's rule decreases by a factor of about 16 when n is doubled. If you see it right here, the errors when n is doubled from 4 to 8 to 16, it gets smaller by a factor of 16. You divide by 16. That's how accurate it is. The Simpson's rule gives us way less errors or smaller errors. Now, we know from earlier formula for the Trapezoid Rule and the Midpoint Rule, the errors on the right-hand side, they're pretty much similar, and we use the second derivative to find k, and we have the third exponent, and one difference was 12 and 24. For the Simpson's rule, the error is a little bit different. We use the fifth power. We have n to the power 4, not 2, and we have 180 right here instead of 12 or 24. That's another reason why it's more accurate. Here's our last example. To find how large should we take n to guarantee that Simpson's rule approximation for the integral from 1 to 2 of 1 over x dx is accurate within 0.0001. It's written down below right here, but for the convenience I'm writing it so I could start down below. Remember the 5 instead of 3, and n to the 4 instead of n to the second. Instead of 12 or 24, we're using 180. So here we go. So we have f of x equals 1 over x, which is x to the power negative 1. F prime will be minus x to the power negative 2. F double prime will bring the minus 2 up front, will make it positive. X to the power negative 3. And the third power will be example number 5. How large should we take n to guarantee that the Simpson's rule approximation for the integral from 1 to 2 of 1 over x dx is accurate to within 0.0001. I do have the formula written down below in red, so let's get started. F of x equals 1 over x, that means it's x to the power negative 1 as a power rule, x to the power n. So I could apply it quickly. And we have this, the first derivative will be minus x to the power minus 2. And the second derivative will be positive 2 times x to the power negative 3. The third derivative will be minus 6 x to the power negative 4. And the fourth derivative will be 24 x to the power negative 5. And that could be written as 24 over x to the power positive 5. But as you could see on the right hand side, for the convenience, I do have this written, which makes sense. If x is greater than or equal to 1, 1 over x should be less than or equal to 1. Which means now we have the fourth derivative of f of x absolute value, which equals to absolute value of 24 over x to the power 5. That should be less than or equal to 24. Of course, if 1 over x is less than or equal to 1, that says the same thing as 1 over x to the power 5 should be less than or equal to 1. Even faster. Next, with that in mind, we could go back and think about the following. That k should be, we could take k as 24. So we can take k to be 24. For an error less than 0.0001, we should choose n so that 24 times 1 to the power 5 over 180 n to the 4 should be less than 0.0001. Rearranging and having n to the 4th on one side, we have the following. N to the 4 will be greater than 24 times 1 to the 5th, which is just 1, over 180 multiplied by 0.0001. Simplifying this and applying the fourth root, n should be greater than 1 over the fourth root of 0.00075, and that is approximate to 6.04, which means we can take n to be 8 because n has to be even, and we can't take 6.04 or even 7. So we need n to be 8. Just a quick comment. Earlier we looked for n such that the error in trapezoidal approximation to be within 0.0001 came up to be 41. For the midpoint with the same accuracy, n came up to be 29. So the midpoint is more accurate. We need less partitions or less number for n to be within 0.0001 compared to the trapezoidal approximation. But what about Simpson's rule? For Simpson's rule, we only need n to be 8 to have the error within the same number, 0.0001. And that should do it. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.